Hello and good day. Today we will present our machine learning project titled Dry Bean Classification. These are the group members. From left to right is Siti Diana, Elia Omaira, and Aida Zahira. For our project, we selected the dry bean dataset from the UCI Machine Learning repository. This dataset contains 13,611 total samples, 16 numerical features, and 7 target classes representing different bean varieties. The task type is multi-class classification. The features are shape-based measurement extracted from bean images, such as area, perimeter, major axis line, minor axis line, compactness, and aspect ratio. The goal of the project is to train machine learning models that can accurately classify bean types based on these geometric characteristics. For the missing value update, we check all 16 features for null values, NaN values, or incomplete records. And after the inspection, we found that the dataset contains 0 missing values across all columns. And there are several reasons why this dataset has complete records. They are because the data was collected through automated images processing. So each bean sample was fully segmented before measurement, and the features were computed directly from images. So because of this automated process, there was no manual data entry, which has reduced the possibility of human error. Therefore, no imputation or data removal was required during pre-processing. For outlier analysis, we used box plot to identify extreme values within the dataset. We observed several outliers in features such as area, perimeter, and major axis line. However, after analysis, we decided to retain all outliers for modeling. This decision was made because first, the value represents real physical measurement. And then, the outliers reflect genuine variation in bean morphology. And if we remove them, it could eliminate important characteristics of minority classes, for example, Bombay beans. Since bean classification depends heavily on natural shape diversity, removing this value could reduce model performance and weaken the class representation. Therefore, all outliers were retained. Next is stage 0B, which focuses on handling class imbalance. We analyzed the class distribution of the training set and found that the dataset is imbalanced. The largest class is the Mason, which represents about 26.19% of the data, and the smallest class is Bombay, with only 3.86%. The imbalance ratio is approximately 0.1473, which is below the required 0.2 threshold. So to address this issue, we apply SMOTE. It was chosen because it generates synthetic samples for minority classes, improve class balance, and help model learn minority patterns more effectively. And importantly, SMOTE was only applied to the training data to avoid any data leakage. Now, on our first exploratory data analysis visualization, we use correlation heat map. So from the heat map, we observe very strong correlation between area, perimeter, and convex area. It has a correlation value greater than 0.9. So this indicates that the presence of multicollinearity among several features. And this is important because linear models like logistic regression are sensitive to multicollinearity. Based on this observation, we recommend feature selection or PCA for future model improvement stages. And this heat map also helps us better understand the relationship between geometric features before training the model. Now, this is our second EDA visualization using a scatter plot of area versus perimeter. From the scatter plot, we found that the Bombay class formed a distinct and isolated cluster with very large area and perimeter values. This suggests that this class is highly separable from other classes. However, we also observe significant overlap between Syrah and the Mason classes. This overlap indicates that these two classes may be more difficult for linear models to distinguish accurately. Other classes like Kelly, Horos, Shekhar, and Babunya show moderate separation in feature space. This analysis helps us predict possible misclassification patterns before model training. For stage A, we implemented logistic regression as our baseline model. We selected logistic regression because the dataset is tabular. It is already pre-processed and suitable for multi-class classification using the one versus rest approach. This model has achieved 91.14% accuracy, 0.9118 weighted F1 score, and a 0.9255 macro F1 score. This result indicate balanced performance across both majority and minority classes. Additionally, 6 out of the 7 classes achieved F1 score above 0.90. And the Bombay class achieved perfect precision, recall, and F1 score. This confirmed that the Bombay class contains highly distinctive geometric characteristics that are easy for the model to separate. This is our Stage A convolution metric analysis. It shows the convolution metric for the logistic regression model. So from this convolution metric, we can see that the Bombay class achieved perfect classification with all 104 samples predicted correctly. And we can also observe excellent performance for Kelly, Horos, Shaker, where each of these classes achieved more than 94% correct prediction. So overall, the model produced only 240 misclassification out of the 2,709 testing samples. So the main confusion occurred between Demerson and Sierra classes. Specifically, 77 Demerson samples were predicted as Sierra and 34 Sierra samples were predicted as Demerson. So this aligned with our earlier EDA findings that show that the scatter plot shows strong overlap between these two classes. Therefore, the confusion metric validates the insight discovered during the exploratory data analysis. And that concludes our presentation for Stage 0B and Stage A of the dry bean classification project.